So hello everyone, I am Indrajyoti Gaine and presently I am pursuing my PhD from Department of Mathematics and Statistics IIT Kanpur, and I am a PMRF fellow, and also I have cleared CSR with 108 rank. Okay, so till last day we have discussed about set, subset, and singleton set. When a set is a subset of another, and when we call a set a singleton set, and how we can say that phi is a subset of all set, and also we have discussed about into other things. Okay, so today we will start with some example of subsets of real number. Subsets of real numbers. Okay, so what are real numbers? Mainly real number sets are defined as R, which is collection of all numbers which are real. Okay, so this contains every kind of set, like natural set, which is containing all the elements like 1, 2, 3, 4, and so on. Rational numbers like this p by q form, where p and q belongs to natural number and q not equal to 0. So these all are collection of subsets of real number. But there are a special kind of subsets of real number, like intervals. Intervals. So what we understand by this term intervals? Interval means there are some starting point and ending point, and we are collecting all points inside the into this range. For say, let a and b be two real number. Let a, b be two real numbers. Then open bracket a and b. This is collection of all those elements in R such that a less than x less than b. That means collection of all those elements of R which are lying inside the range a and b. Maybe that is the elements which are larger than a but smaller than b. We are collecting all those elements. Now, point out one thing, that in this set, this is obviously subset of R. Why it is subset of R? Because we are collecting an elements of R with some restriction. So obviously these all are elements of R. So automatically this is a subset of R. Like whatever we have discussed in the last class, like if x belongs to, y belongs to open interval a comma b, then obviously we have this condition. But before that we have this condition, and this condition implies y belongs to R, and which together implies this subset of R. Okay, so up to this thing we are clear that this is subset. By this statement we are clear that this a open bracket a comma b is a subset of R. Okay, now point out one thing, that in this set, okay, in this set we haven't included 2 points a and b. Okay, check that a comma b not belongs to this set. So if I include one of the a or b, like if the set is like this, set is in this form, like x greater equal to a less than b. This will be denoted like closed bracket a open bracket b. Okay, if the set is as the form like this, x subset of R such that a less than x less than equals to b, then the set will be of the form a comma close interval b. And if we include both the points, if we include both the endpoints, then it is called a closed set, or it is denoted by closed interval a closed interval b. So this closed interval stands for that set contains the endpoints. Okay. So if the set is like this, a comma b, then this set contains the end points. This set does not contains the end point. Okay, and for this open interval a closed interval b, this kind of things, we can say the set does not contain left end point but contains the right end point, and vice versa, like the set contains the left end point but doesn't contain the right end point, like this. Okay, so these all are subsets of R. So let us define this set. Take an example. You can say this is an example. Example. The set of all. Okay, positive. Set of all non-negative real numbers. That is the collection of all those sets, all those elements of R such that x greater than or equal to 0. So we denote this set like it okay, how can I denote this set? So it contains all positive plus 0. Okay, I mean that means it doesn't contain the non-negative terms. Sorry, it doesn't contain the negative terms. But in non-negative term, we can consider all the positive real numbers and also 0, because 0 is not a negative number. So this set can be written as 0 up to infinity. Now, open bracket or closed bracket, it contains the element 0, so closed, but it doesn't contain infinity, so open. Similarly, if I say the set of all non-positive real numbers, then that can be defined as minus infinity 0, minus infinity 0. Okay. So if I say set of all positive numbers, then the set will be like this: 0 to infinity. Zero to infinity. Why is this so? because here we are collecting the set of all positive numbers. So 0 is not a positive number. 0 is non-negative, but we can't say this is a positive number. So we are taking open interval 0, open interval infinity. So one can ask that why we are taking infinity as an open interval, because we can't include infinity, because we don't know what is infinity. Infinity is just a notion. We actually we are saying like there are no finite terms of where we can end. So that's why we write this infinity. But this is not an exact term that up to this step we can say this is infinity. So that's why we write it like an open interval, because we can't end that point. Okay. So let us take another example. Okay. Example one. This was example one. No, this is example two. Example two. So let us take three set. So b equals to is 2. Okay, one other static. Minus 9. Okay. Okay. So question is find the subset relation among these sets. Okay. So what is the question? Question is we are given with 4 sets. Now we need to find the subset relation among them. Like it can happen that C may be subset of D or B may be subset of C, like this kind of thing. So we need to check that which condition is true and which condition, which one is subset of which one. Okay, so let's start from A. If X belongs to A, first start with A. If X belongs to A, this implies X is a real number and X is less than 5, greater than 3. Now, if this so, then we can obviously say that this implies minus 7, minus 3, X, 5, 9, which means X is less than 9, greater than minus 7, which implies X belongs to B. Therefore, A subset of B. Similarly, we can show B is a subset of C. Why is this? Just think once. Every element of the set B is obviously an element of C, but C has an extra element. Which one is that? Minus 7. So, note one thing, that we can't say B equal to C. We can't say this. B is not equals to C. But the combination is true. Equality is not true. Okay. Similarly, one can easily check C. Sorry. C is a subset of D, which is easy containment relation, because one can easily check that how it is coming or not. Okay. 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 So we have already seen the how can we can write a set like this. So note this thing first. Then we can write a interval like this form. You can write an interval in this form. Like, okay. Okay. So an interval. What is different between an interval and a singleton set? So in a singleton set, we are writing a set like this. Okay, singleton set we writing is an element. I will write it in a second bracket. This is a singleton set. Singleton set and AB, 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 or these all are called intervals. Okay. Now the thing is, uh, one can ask that what is the length of this interval? So why this concept of length is coming? Because in future, if you go with higher study, you can see that we are very much worried about measures, or whenever we do the integration, then we need something called measure, like in which interval or we on which thing we are doing the integration. So for that purpose we are very much interested about measure, like in your class 10 you have already discussed about an area of a square, area of a cube, or length of a line segment. So this those all are measure. So why those things is required? Because in measure theory, using measure theory or using this measure, we are doing our integration. Whichever we are doing in already have done some integration in your class 10 level. So the theory developed around these measures. So that's why we are very much interested about this measure. So for that, we can talk about the length of the intervals. So if I consider the length of each of this set, so what will be those? So the length of the set AB is B minus A. Okay, not like two bracket. It may be little confusing. Okay, length of this interval equals to B minus A. Like it's the length of the distance between A and B. The distance between the points A and B. Now one can think that there are three kind of or four kind of distinct intervals. So the length must be different. Like for this set, I have been discussed. For this one, we have discussed like this. But what about this? What about these three sets? So these three sets have same length as A comma B. Why? Because singleton set has measure 0. How? How singleton set can have measure 0? Because if length of this set is like this, so length of singleton, this is nothing but A minus A, which is equals to 0. Because the starting point and ending point both are same. And we are just deducting the end point and starting point. So this must be 0. And if I say this set, this is nothing but singleton A, and this. Like if I okay, we will come back to these things later. But Just remind that this has length b minus a, length of this equals to b minus a, and the length of this set is also b minus a. That means we are just deducting the ending point and starting point to get the length of a subset of real number. Okay. Now come to the point power set. Power set. Okay, so what are power set? So at first, keep some space for definition. Let us see some example. Let A be a set. 1, 2, 3. Okay. So note one thing, that we are putting second bracket in this kind of thing, and for first bracket and third bracket for intervals. Why this is so? This is because in this, whenever we putting second bracket, we are just including some singleton set. That is, each element of this set are individual one element. But whenever we are putting this first bracket or third bracket, in there we are including the whole range. We are not including the particular two element or three element. We are denoting the whole range, where the endpoint may be included or may not be included. But in the case of second bracket, we are just taking some particular elements A, B, C, or 1, 2, 3, and we are done. We are making this as saying as a set. Okay. So if A be a set, then this set is contain three elements: 1, 2, and 3. So what are the subset of this set? So subsets of A equals to, one is phi, because we have already discussed that phi is a subset of every set. In the last class we have discussed this thing. Okay, singleton 1, singleton 2, singleton 3, 1, 2, 1, 3, 2, 3, and we already know that every set is subset of itself. So these are the collection of all subsets of A. So if I collect this as a subset, as a set, then this is called the power set of A. Power set of A. So by definition, we can say, for definition, we can say the collection of all subsets of a set of a set. If a set is a term of a set A is called the power set of A. Okay. The collection of all subsets of the set A is called the power set of A, and it is denoted by P of A. Denoted by P of A. So By this example, we are clear that we are collecting all the subsets of A and we call it as a power set. So, okay. Similarly, we can find all subsets of any set, whichever set you give, we can find the subsets of all elements. Now, one can ask that suppose a set has cardinality 4, like n of A. In this example, n of A equals to 3. And if I find n of P of A, this is equals to 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 8, which is nothing but 2 to the power 3. So, note that if n of A equals to m, then n of P of A then n of P of A equals to 2 to the power m, where n of A stands for the cardinality of that set. Okay, so in similar way we can find the power set of every set. For every given set we can find the power set of that, but in case of real number or which are like we don't know all the elements, for those case the power set can be infinite and we can't write all the subsets explicitly, but yes, there are some concept called power set. So you can just write a power set. But one thing, just note that in every power set, the set itself and phi must be an element. Okay, for any set, for any given set A, P of A must contain at least two elements, phi and the set itself. Like whatever set we take, like if we take suppose B equals to B equals to the singleton set A. No, not like that. Singleton set 5. Then the power set is like 5 and singleton 5. And why we are putting the second bracket? Because we know the exactly how many elements are there, or you can say that we can explicitly write each element of this subset or of this set. Okay, so we can explicitly know each element of this set P of B. That's why we are putting second bracket. But if we don't know like that, so we will write open bracket, first bracket or third bracket to denote the interval kind of things. Okay. And also you can check that as n of B equals to 1. N of B equals to 1. N of PB is equals to 2 to the power 1, which is nothing but 2. Okay. If B equals to 5 itself, then what will be P of B? This is nothing but the element 5. So see the thing, difference between these two things. Here it is 5 and here it is 5 under second bracket. So if I check n of B, what will be this? This is 0. This must be 0 because 5 contains no element. But what is n of P? This is not 0. This is 1, which is nothing but 2 to the power 0. But why it is 1? Because note that this set contains the element 5. That's why we put second bracket, and 5 is an element of this set P of B. Okay, so itself 5 is nothing. So that's why the n of b equal to 0. But n of pb equals to 1 because it contains p of b contains one subset which is 5. Okay, I hope up to this clear. Okay, we have done all these things. Okay, so let us talk about universal set. Universal set. So before discussing universal set, let us discuss about the term universe. So we are all familiar with the term universe as we are all a member of the universe of Earth, planets, and we know that universe means the whole total our Earth and all planetary system and all the stars and all we call it universe. Okay, so like that. Similarly, we talk about universal set for some given set. Okay, so actually in set theory, universal set is a set which contains all objects including itself. Okay, so let me write it. A universal set is a set which contains which which contains all objects including itself. Okay, then universal set is a set which contains all objects including itself. Okay, so in case of set of all integers, if I take set of all integers for the set of all integers, the universal set can be the set of all rationals or set of all real numbers. Okay, so in case of the integers, the universal set can be the set of all rational number or set of all real numbers. Okay. So actually this concept is not that much rigorous because this is not properly defined that this is the unique or something like that. But yeah, we can think like the universal set is the father set of some set, like the where it is contained, or where the all the subsets of that set contained. So that that set can be called a universal set. Okay, like we are including in the our universe like that, like this thing. Or nowadays you are all familiar with the Marvel universe. So we call it Marvel universe or DC universe. So in that case, we are calling that Iron Man is a part of this universe, or Batman is a part of this universe. Like that, we are calling a set and a set of integers. This is an element, or this is an member of some universe or rational numbers or universe of real numbers. Okay. So let us take one example. One example of this. The example is saying that A is a set 1, 3, 5. B is a set 2, 4, 6, and C is a set 0, 2, 4, 6, 8. Now we have to find which one is the universal set of this set. So the question is, which of the following is a universal set? Universal set for all these three sets. For all these three sets. For all these three sets. So one is 0, 1, 2, 3, 4, 5, 6. Second one is 5. Third one is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and fourth one is 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we need to find which one is the universal set of all these three sets. Okay. So first of all, check that which of this collection, which of these sets contains all A, B, C together. To just need to find that set only. So check the first one. A is contained in this set clearly because 1 belongs to the set, 2 belongs to 3 belongs to the set, and 5 belongs to the set. But check C. C is not included in the set. This one. Okay. So why it is not? Because 8 is an element of C, but 8 is not contained in the set 0, 1, 2, 3, 4, 5, 6. Therefore, we can say this is not an element of. This is not an universal set. Similarly, 5 is not universal set, and by similar logic, this is not a universal set. Why? Because 0 is an element of C, but 0 is not subset of this set. Therefore, the only option is this. And you can check that all the sets A, B, and C are subset of this set. All these A, B, and C are subset of this set. Okay. So thus you can find a universal set of a given set. We can follow by following the instructions. Okay. So next topic is our Venn diagram. So Venn diagram is a process where how we can define how we can discuss about the set. Like most of the relation of this set can be represented by means of this diagram. And this diagram is actually named by the logician, by the name of logician John Venn. And usually we use the two rotation like a circle or a square. circle and square. This stands for the set and subset, and this stands for the universal set. So first take some example. There is no definition kind of thing, but we can say that this is there is an example like this is our universal set R, and the subset natural number. Or we can think like this. This is a universal set. Okay. Rational numbers Q, and this is our subset natural number. Or for example, if I take the set like this, if we say take U equals to, let's take U equals to 1, 2 to up to 10, 1, 2, 3 up to 10. A equals to 2, 4, 6, 8, 10. B equals to 4, 6. Then one can clearly see that B is subset of A and both are subset of U. So this can be written as Venn diagram like this. This is our universal set U. Under this we have a subset called A, and under that we have a subset called B. So B contain 2, like 4 and 6. Now B and A both contains 2, 8, 10. Okay, so these 2, 8 and 10 are outside B but inside A. And which are the elements which are not also in A and B? Those are like 1, 3, 5, 7. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, 9. So these are the points which are in universal. So with this, by this process, we can define the Venn diagram of given universal set, given subset, and all these things. Okay, so this thing helps us to. So why? What is the use of the Venn diagram? So Venn diagram usually helps us. Okay, let us write this thing. Venn diagram helps us to understand the operations. Okay, understand the operations on sets. The Venn diagram helps us to understand the operations. Okay, operations of on sets. So we will see, for example, on after some time or next day. So usually help the operations of sets. To understand those things properly, we will use these things. So before that, let us define some operations on sets. Operations on sets. Okay, so at first Union. Union means collection of all elements which are contained in both. So take example, then it will be easy to understand. 1, 2, 3, 4, 5, 8, 9, 3, 7. So we define this like A union B. So this notation stands for union. Okay. This notation stands for union. A union B. This is nothing but the set 1, 2, 3, 4, 5, 7, 8, 9. So by definition we can say A union B is a collection of all those elements X such that X belongs to A or X belongs to B. Okay, so A union B is the collection of all those X such that X belongs to A or X belongs to B. So if I now one can think like that, if A equals to 2, 4 and B equals to 4, 6, 2, 9, then what will be the case? Here we can say that A subset of B, but that doesn't matter which is subset of which one. We are not bothered about these things right now. So A union B is the collection of all those elements which are in A or B. So in A there are 2, there are 4, but these are complete. So A set is complete. Now go to B. So we have 2 in the set B, 4 in the set B. What rest are there? 6, 9. Okay, so this is our A union B, and by this we have found one thing, that if A subset of B, then A union B equals to B. Okay, and vice versa, like if B subset of A, then A union B equals to A. That is nothing much important like that. You can deduct this thing. Okay, so next property is intersection. So let us take the first example, first two examples. So it will be easy to understand both the things. Okay, what is A, B? One, 2, 3, 4, 5. B equals to 8, 9, 3, 7. Okay. So what about A intersection B? So in this set, we are collecting all those elements which are common in both A and B. So find that there are only one element which is common in both A and B, and that is the element 3. This element 3. So what is the definition of what we can define like A intersection B? So A intersection B is the collection of all those X such that X belongs to A and X belongs to B. Okay. So let us take another example. There given A equals to 2, 4. 2, 4. B equals to 2, 4, 6, 9. 4, 6, 2, 9. Okay. 4, 6, 2, 9. Then what is A intersection B? Then A intersection B is nothing but 2, 4. And by this it is clear that if A subset of B, then A intersection B equals to the singleton set A. So we already have found two properties, and today we will see these two properties by Venn diagram. Okay. Okay. So let us draw the Venn diagram for these two things, and after that we will discuss another thing. Okay. So let us say this is the set A. A is set this one, and this is the set B, and this is the universal set U. This is the universal set U. Okay, so A contains the red one. Okay, the red one. And B contains the blue one. Okay. Okay. So what about A union B and what about A intersection B? So A union B is nothing but like this. Okay, A union B. All the elements like this. Okay, so we can just rub this thing here and we can say like this. So A union B means all the elements in this set, and it is A union B. And what about A intersection B? So always we will draw some universal set notation. Okay, and this thing will be like this. So we are drawing. So it is not that matter that the drawing is perfect or not, but just you need to be rigorous about the idea. Okay, and this is the A intersection B. Because you can clearly see the colors that in case of A union B, we are concluding the three proper things like whatever inside A, whatever inside B, and whatever is there common. So we are taking all the elements. But in case of A intersection B, we are considering all the elements which are common for both the set A and B. So by this Venn diagram, we are clear that what is A union B and what is A intersection B. Now, if the set is like this, if the set is like this, this is our U, this is our A, this is our B. You can draw this to be a different color. It will be fine. This blue is our A, and the red is our B. Blue is our A. Okay. Blue contained with blue some blue elements, and red contained with some red elements. You can say. So one thing we can clearly see. Okay, so one thing you can clearly see that A and B are not, they are disjoint. Okay, so whenever we are considering about A and B which are disjoint, then they have no common element, right? They have no common element. So in that case, if we take A union B, Then this is our U. A union B will be the all the collection of all sets, right? But there is the problem. But what about A intersection B? U. This is our A. This is our B, and there is no common intersection. So, in that case, A intersection B equals to 5. Okay, you can clearly see that there are no common point in both the set. If we want some example, one can think like this: 2, 4, and B equals to 5, 6. Then A intersection B equals to 5, and A union B equals to 2, 4, 5, 6. Okay. So by this you can say that when two sets are disjoint, then the intersection is 5. If two sets are disjoint. Okay, and also check the Venn diagram for the containment relation. Like if I say that like this, this is our U. This is our blue A set, and this is the B set. So A contains all the blue elements like this, and A contains B contains the red elements. So here the containment relation is there, that is B subset of A. Okay. So what about A union B? This is our U. And what about A union B? This is nothing but the set A. Why? Because we are including all the elements of A and B is already inside A. So it is sufficient to include the element only A. And what about A intersection B? Only the elements of B. This is sufficient because you can clearly see that B intersection A equals to B because all the elements of B are already inside A. So if I take intersection and if we are restricted to only the common elements, then we will come up with the elements of B only. So thus A intersection B equals to B, and by this Venn diagram, it is clearly we can see that how we can easily see the set operations with the help of Venn diagram. Okay, so that's why Venn diagram is that much important because in many cases it is difficult to study the whole set, but it is quite easy to discuss the Venn diagram and we can understand the properties of the thing. Otherwise, there are in next class we will discuss about some more properties of the state relations, and from that we can clearly see that whenever we don't use Venn diagram, it is very difficult to find some interpretation between the operations. So that's why Venn diagram is that much important. So today lecture we will end here, and from next day we will see some operations of this union and intersection. Okay, so okay, let us finish here.